All right, so we talk about Diffie-Hellman key exchange, and we talk about some of the hard problems like discrete logarithm problem and factorization problem. So let's look at RSA, which is an encryption algorithm whose security depends on both factorization problem, but also discrete logarithm problem. Okay, so let's see it in its basic form. Key generation part is done only once. So every user actually performs their key generation steps like this. They randomly choose big primes P and Q. Then compute P times Q, which is N. So multiplication is easy. So here we will rely on the hardness of the factorization problem because we will publicly announce N and we will assume that people will not able to factorize it and obtain P and Q. Okay? So then we choose a public parameter E. This can be something as small as 3, or sometimes we choose 2 to the 16 plus 1, which is 1, many zeros, and then 1, which allows us to perform operations in an efficient way. Then we compute the inverse of E modulo P minus 1 times Q minus 1. Here actually the term will be phi n, but instead I wrote the result of phi n because it is the multiplication of 1 minus these primes. Okay, so you need to calculate the inverse of E with respect to this modulus. This means that you will calculate a value D so that D times E equals to 1 in this modulo. Okay, since these are going to be large numbers, you might ask if it is easy to find an inverse in this huge group. But there is an algorithm called extended Euclidean algorithm, which actually calculates this in a very fast way. So now we have some parameters N and E, and these are public parameters, which we call public key. So N is referred to as RSA modulus, E is referred to as RSA exponent. So you can always receive these parameters. Okay, even in certificates, you can easily find them. Now the private key is D. But also, we have to keep P, Q, phi n, which is actually P minus 1 times Q minus 1. We have to keep all of these secret because if you explain P, then they will find P and Q, right? Then they will calculate P minus 1 and Q minus 1, so they can find the inverse of E like D, and they can capture a private key. Okay, so this is why the security here depends on the hardness of factorization problem. But there are sub-exponential time algorithms, as I mentioned, so we have to choose N as a really large number. So we need to choose large primes, so their multiplication will be N. And here we're talking about at least 3072-bit integers. So how the encryption works? Somebody wants to send you the message M. So it is going to be in modulo n, so you actually divide your message into small pieces, so it will be smaller than n. Okay, so the person who wants to send a message to you actually calculates e power of n, where e is your public key, right? And calculates as modulo n. Again, n is a public parameter, so they end up with the value c, and they send c to you. Then you calculate the d power of c. Since c actually m to the e, calculating the d power of it actually ends up with m to the power e times d, right? But d is the inverse of e in this modulo, so due to number theory, this would actually give you m. Okay, so here actually we are using a very basic trick in number theory. So anybody wants to send you a message actually calculates the e power, and you decrypt it by using calculating the d power. So two things to mention here. One thing is that, as I mentioned, this is the basic form, and we don't use it like this because whenever I want to send a message, I should choose a random number and add it to the message to create a noise, because if I don't do that, somebody who's, for instance, you said hello as your message and send C, okay? And the person decrypts. Now we can always perform replay attack sending the same C again and again, okay? And they will think that everybody is saying hello to them. So without knowing M, we can send the same message. This is the problem. This is why you choose a random value for every message. So there's some padding involved, and there are some standards for it. Another thing we need to focus is that the choice of E. Okay, so but we currently observe many bugs in practice, like in Java or in OpenSSL, and it turns out to be that the implementations actually, overlook some of the basic definitions. For instance, as I write here, I said that E should be larger than 2, right? For instance, some people think that there's no need to check this. This is obvious. So in their code, they don't check this. Okay, actually, you have to always check the domain parameters. So for this reason, go to GitHub and you will realize that there are many RSA implementations where E equals to 1. But if you choose E equals to 1, when you want to encrypt a message, you calculate the first power of it, which is the message itself. So you actually send your message as a plain text. And the decrypting person also calculates the first power of it, which is the same. So they think that it really works really fast. So this is why they stick to choosing E equals to 1 and actually start talking in an unencrypted way. Okay? Yes, choice of E affects the performance, but you cannot choose it less than 2. Okay? So this is also the easiest way to put a bug in many systems. So create a Stack Overflow entry. Ask, for instance, say that you want to use RSA and ask if there's a nice implementation or fast implementation in any language you want. Then as a new, create a fake account and answer this question, giving the link of your GitHub repository, which actually involves a bug like E equals to 1, and then everybody starts using your backdoor implementation. So here we have to actually talk about something. So I explained everything here, and it looks like basic and meaningful, but here actually there's a problem. I start with saying choose 2 random primes, and they have to be big. So how can you choose a big number and be sure that it is prime? So you can say that I can randomly choose an odd integer and check if it is prime number, but this also means that, factoring it, right? So if it is easy to perform factorizations on these numbers, then why would it be hard to factorize this, right? So there should be a way of checking the factorization of these numbers, but it should be very hard for the attacker. So this looks like a paradox, but it is not a paradox because here the 2 types of the problems are different, because we actually can divide these problems as the decision problem and the search problem. So a decision problem is a problem whose solution or output is yes or no. Okay. A search problem is a problem whose solution can be more than yes or no. Okay. So here's an example. A search problem. I give you a number n and I ask you to factorize it. A decision problem, I give you a number n and ask you if n is prime. So you might think that both are identical because, for instance, if I solve the search problem, then this means that I already solved the decision problem, right? Because when I factorize it, I know if it is prime or not. But question is, if this one is easier than this one, so can I determine that a number is prime or not without factoring it? So this is counterintuitive, but the answer is yes. So this is why we have a polynomial time algorithm for this and sub-exponential time algorithm. This is why RSA works in practice, okay? So parameter selection for RSA. Here I'm going to talk about primality test. As I mentioned, P and Q should be generated randomly. In standards, a random number generator, which is a combination of a physical random number generator and a deterministic random number generator, is used. So you randomly generate a number. If you randomly select an odd 512-bit number, it's prime with probability 1/355. So most of the time, your random number generator will give you a number which is not a prime. And actually, we are going to work on larger bits, actually. So you have to perform some primality tests to be sure that P and Q are really prime. And in practice, some people fail this, okay? You can actually go to internet, download all of these public RSA parameters, and check if they're really prime. And most of the time, you will realize that they are not. And if they are not prime, you can factorize it, then solve this factorization problem for both of these divisors, and then use Chinese remainder theorem to, combine these two solutions and obtain the secret key. So, one of the primality tests you can use uses AKS algorithm, Agrawal, Kowal, and Saxena, because this is a polynomial time algorithm to test for primality. This algorithm was found in 2002. It was a breakthrough, but the thing is that we don't use it in practice, because even if it is a polynomial time algorithm, when we work on with large inputs, it really takes a lot of time for this algorithm to give you the results. So, yes, AKS is too slow to use in practice. For this reason, in practice, we use randomized polynomial time algorithms. Okay, so let me explain what a randomized algorithm is. So sometimes we actually categorize algorithms like Monte Carlo algorithms. A yes-bias Monte Carlo algorithm is a randomized algorithm for a decision problem for which the yes answer is definitely correct and the no answer is incorrect with a probability at most epsilon. So you run this algorithm. If it says yes, it is correct. If it says no, then it is correct with some probability. So with a randomized input, you rerun this algorithm and again and check if it gives you the no answer for many inputs, then you will be confident that most probably the answer is correct. There's also Las Vegas type algorithms in which the answer to a decision or search problem is an algorithm. So a Las Vegas algorithm to answer a decision or search problem is an algorithm whose answer is definitely correct if it finishes. So sometimes you run it and it goes forever and doesn't give you an answer. So here we are going to talk about Monte Carlo type algorithms. So Fermat test is an example to this. So Fermat test work like this. So you are given an odd n. Recall that in RSA, this equals to P times Q, multiplication of two primes. But you don't know this P and Q, right? So you want to check if n is prime. Sorry, I go back. You choose randomly P and Q. So instead of n, we have P here. Okay, we want to check if this odd n is prime or not. What you do is as follows. You randomly choose a number a, integer a, then calculate a to the n minus 1 modulo n, and check if it equals to 1. This is important because Fermat's theorem says that if n is prime, this is correct, okay? Because if n is prime, any number to the power n minus 1 should be equal to 1 modulo n when n is prime. So if this doesn't give you 1, you say that this cannot be a prime number. Because Fermat's theorem says that when n is prime, this is correct. So if recall that we start randomly choosing P and Qs, right? So you randomly generate one of these P and Qs, come here, choose a random number a, calculate a to the P minus 1 modulo P, and check if it equals to 1. So if it is not, then P is not a prime number. But if it is 1, then the answer is true with some probability, because you might be unlucky and might be a composite number, but this equation might still hold. So what you do is as follows. Repeat this process, then choose another A and check the equality. Choose another A and check the equality. So it gives you 1 many times, then you will say that most probably this is a prime number. Okay. So there are other tests, Holloway-Strassen test. You do similar thing here. Instead of calculating n minus 1, you divide it with 2 and check if it equals to this one. And this is not actually A over P. This is Legendre symbol. So I'm not going to go to detail. But this test, again, tells you that this number is composite if it doesn't hold. But if it holds, then it is prime with probability close to 1 over 2. Okay. So When we combine these two ideas, you end up with Miller-Rubin algorithm. So this algorithm uses the similar ideas. The answer composite is definitely correct, and the answer prime is false with probability less than 1/4. So what you can do is choose many random input A and repeat this process. So if the test answers m times n is prime, so m many times the result is prime in succession, then the probability that n is composite is less than 1/4 to the power m. Okay. So today the test applies at least 25 times. So after 25 random input, if the algorithm tells you that it is prime in all of them, then it is prime with probability 1 minus 1/2 to the 50. So you should be very, very unlucky that the test fails. Okay. This is important again, because in practice, people use RSA and think they are secure, but their choice of P and Qs most of the time are not prime numbers. Okay. You have to check if they are prime. So you should actually have a fast implementation of this algorithm and check if it passes this test.